six-sided die twice, so what is the probability of the value that the first roll is strictly less than the second roll? Okay. The question is, this is the basic problem, but the first question that is important is, when you're solving a probability problem, what is the experiment? So do you know what is the experiment? Can you explain it to me? What the experiment is all about here? So probabilistically, it's a different experiment, right? So what's the
A
experiment?
certain action to get certain outcomes.
Yes. So what is the experiment here?
Rolling of six-sided die twice.
Exactly. Let's write it down. Yeah, this is trivial things, but you will understand that as you solve harder problems, the trivial things are the ones actually break or build your problem. Okay. The next, good. This is great. So next question is that, what is the sample space? Um, so the next question is that, what is
Yeah.
the sample space? Yes.
One,
So yeah,
one, one, one.
right. So the sample space is high Sreni, 1 comma 1, 1 comma 2, right? Dot, dot, 4 comma, sorry, 6 comma 6. So how do you represent it mathematically? We represent it mathematically as the set builder notation, I comma j, I n. I hope you can see the screen, Anisha and Srinivas,
Yes.
where I comma j is I and j are in 1, 2, 3, dot, 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 6, right? Right. So why is sample space super important in the probability theory? Because when in 1800s, as I remember now, when the gamblers in France, the French gamblers like Pascal and others, where those are the people who discovered probability, right? Those people are playing the gambling, and they thought that they were trying to understand that what was their odds of success. And when they try to understand that, they realize that it's kind of proportional. It's kind of related to the total number of options available. The less number of options available, the highly likely that they want to get what they want to get, right? And so that's why the sample space is very important, because it tells you that larger the options are, the lower is your chance of getting something. Sorry, it's my 6 a.m. alarm. Okay, so yeah, it's 6 a.m. at US right now, but so happy to do the things I love to do when I wake up. Okay, so the next question is, what is an event? So define an event in that case. Anyone? Srinivas or Anisha? What is an event? So we are discussing this problem, Srinivas, that we are rolling a six-fair die twice. What is the probability? But we are trying to unroll it step by step. So Anisha, what is an event?
A subset of sample space.
Very good. Subset of a sample space. Just to let you know that event E is nothing but subset of the sample space. But just to let you know that all subsets of, in this case, all subsets of S can be up an event. But in general, it is not so. In general, any subset is not an event. Hi, Vedant. For example, there is something called Vitali sets. Okay, like this. You can read it out. Uh, which which cannot be assigned a probability. In other words, which is not Lebesgue measurable. Let's not go into that, but this is just to get an idea that, for example, Vitali sets. Okay, it's not just, you cannot assign a probability. So, but in case of discrete distributions, or discrete sample space, where these are no points, any subset can be uh, An event. And so we kind of see that something is an event when we kind of say that something is an event when we can assign probabilities to it. Okay, like good event is something when we can assign probability to it. Okay, next question. So the next question is about, just give me a minute. So the next question is about which event is specifically interested in? Which event are we specifically interested in? So my goal is, again, for those who are joined right now, my goal is to discuss simple aspects of this problem, because that you can use this framework, you can use these steps and put it for a difficult problem. I will give you now, I will help you understand such a case. Okay. Which event are you specifically interested in this case, guys? Srinivas, Anisha, Vedant, Ayushman. Which event are we specifically interested in here?
I comma j such process such that I use less
Sorry, can you come again, Srinivas?
than I comma j in
Okay,
uh,
so
1 to 6 cross 1 to 6 such that I is less than.
very good. So it's, of course, it's a subset of this, so it will be I comma j, but here I comma j are all in this 1 2 3 6. But in this case, I will be less than j. Okay. So here we assume that I is the first die. I belongs to first dice and j belongs to the second dice. Okay. Okay, super. All of you on board with this? Anisha, Vedant, Ayushman, Srinivas. Srinivas, of course, said this. Did you understand this, guys?
No,
Yes.
I principally just joined now, so
Yeah.
I would do
So,
this.
Ayushman, so we are discussing this problem that we are rolling a fair six-sided die twice. So the probability that the value of the first roll is strictly less than the value of the second roll. Yes, you can. The answer is very easy. It's 15 by 36. But the question is, I want to imprint the framework of thinking probabilistically in your mind forever. Okay. So what are the questions that should you always ask, whether it's a easy one, easy problem or a hard problem? Okay. So the first question we asked is that what is the experiment we are doing here? The rolling the six-sided die twice, right? The next question is that, like, how do we quantify the experiment? It's nothing but the outcomes of the experiments. That is the sample space. So when we define the outcome of the experiments as this, the first one, but the we want to do it more mathematically, and this mathematically doing it has a lot of advantage in the long term, and we will see that. So we write it as a set builder notation. So this is called a set builder notation. These are all high school knowledge. Me revising. It's I comma j, where I and j are this. Also, as Srinivas has said, it's a Cartesian product. And this Cartesian product is very important to understand, because so if you want to visualize this, this is very important. If you want to visualize this, how will it look like? If you want to visualize this, let's see. Uh, if you want to visualize this, it will be like this. Let's see if I can draw. Yeah, perfect. I can draw. So if you want to visualize this, it will be something like this. This is the x coordinate. This is the y coordinate. And it will be something like this is 1 here. This is 2 here. This is 3 here. This is 4 here. This is 5 here. This is 6 here. Similarly, this is 1 here. This is 2 here. This is 3 here. 4 here. 5 here. And 6 here. So this is the first die. This is the second die. So this is the first, and this is the second. Outcomes. So every point will nothing be but this, like each of the points here, I comma j. This is I, this is j. So it's kind of a rectangle. Okay. So you can say that. So it's kind of a rectangle. Like one point is here, one point is here. I hope all of you understood this. All of you understood this? This is how the sample space is looking like geometrically. And this is nothing but the Cartesian product.
So principally, it's like all the way 36 outcomes, like 1, 1, 1, 2, 1, 6,
Exactly.
2, 1,
So
2.
just exactly. So just now you have that's the whole idea. If you've done it geometrically, you see that it turns out to be 36, right? Because you have done it geometrically. So this is the how it looks like the Cartesian product. It's kind of a square here. In general, it will be a rectangle, right? All of you understood this, guys? Any questions? Great. So yeah, so that's a great thing here. How many elements are there? Elements are there in this sample space. As you have said, it's a rectangle. Uh, and each has 6 elements. So total 6 into 6 elements, kind of discrete area. Okay. So now the question is, the main question is that there's some principle that we're using here, and as I said, this principle will go for a larger distance that you can possibly imagine right now in your mind. What do I mean by that? So here we're using something called a multiplication principle. And this multiplication principle is exactly there in conditional probability too. Okay. Or conditional random variables too. The same multiplication principle. But here, it's not evident, but you will see that right now. So what we are doing here is something like this. So let's again build a picture. Pictures are beautiful. Okay. So what we're happening is that you can now, so just like Feynman, Richard Feynman, I hope all of you know him, right? So Richard Feynman had some diagrams. Richard Feynman had diagrams like this, for which he was famous. It's called the Feynman diagrams, and it actually helped people to understand the particle physics in 1,000 times better way. What my goal is to help you understand probability using these diagrams so that you remember it forever. For example, how do you optimize the information that is here of Cartesian product? You can think of it like, I usually think of it like, let's not diagram here. Let's see, I think I can do it here. So you can think of it like C1 or S1, comma S2, the two sets. And I represent it like they're independent with each other. So it's both arrow. That means they're independent with each other. Okay. Like this notation. And the first bracket implies, so this means they are independent, and the first brackets means that they are that the order matters. And when you're taking a tuple, I comma j is different from j comma I. So when this happens, it's kind of And in this case, the tree diagram is the most important. So what is happening is simple, a tree diagram like this. So you can say the first die outcomes and the second die outcomes. And they're independent. So you can kind of, what you're essentially doing here is, sorry, is this. Okay. We are essentially doing this. So here we have 6 options. You can think of it like this: 6 options, 1, 2, 3, 4, 5, 6. And we have 6 options here. Now I'm doing this again. I'm telling you, this exercise I'm doing with you, it seems very simple, but this will be the breaking or building situation for you to solve any problem. Okay. So this diagram will be very useful to each one, every one of you. Okay, makes sense, guys? All of you? So this, remember this structure. The structure is super important. Okay. So the next question. Which event we are specifically interested in? The event we are specifically interested in is this event. This specific event E is I comma j. So if you now try to understand a subset of it, so let's try to visualize it. In this visualization, I comma j. So this is, let's call this I, because it's the x-axis. Let's call this j. So what do you mean by I comma j geometrically? Anyone? I less than j. Which one will be I less than j? Tell me. So this is 1 comma 1. This is 1 comma 2. 1 comma 3. Anyone?
Where both I and J are not the
But
same
not
or
friend.
something.
Sorry, someone said it didn't didn't understand. Sorry, who?
Where J, as we go vertically upwards, J is not greater than I.
Yeah. So do you have a specific region in mind?
Yeah, top friend.
Yes, the upper half triangle. So this line is x, y is equal to x. This is I less than j. Right. J is greater than I. The x-axis y. Sorry, this is an extra part I did. The x-axis is, the y-axis is greater than x-axis. This point is y is equal to x line, and this is I, j greater than I. So you can say that this is I less than j. This is, we'll do it another thing, I greater than j. So I hope you understand how to get I greater than j now. We will make it absolutely green or maybe blue. This is I greater than j, the lower half triangle, right? All of you understand this, guys? Questions? This is I less than j, I greater than j. And this middle one will be I equal to j. Probably this one here. All of you got it, guys? Yes or no? Questions? Anisha, Ayushman, Vedant. Questions? All of you understood it? I like to listen your voices. To your
How
voices.
do we?
Yes.
Probably this isn't the question, but how exactly do we choose the event? Like I, comma j. In this case, I is less than j.
Very good. That's a. I mean, do not ever think, Ayushman, that your question is not valid. Okay. So first of all, an event is a subset of the sample space. Okay. That's how you define an event, and all
Mhm.
subsets of S can be an event in this case. But in general case, because you see that as I was telling the students out here that an event as a sample space is a set of options. So when in France, Pascal and other mathematicians were gambling, and they realized the more options they have, the less chance of them winning. So what do we mean by winning? By winning, they mean that I have, if I get this set of cards out of this large possible set of cards, that means I win. So they started to define probability in a classical probability way. That probability is defined as classical probability as defined as P of an event. E is nothing but the number of elements of the events divided by the number of elements of the total sample space S. That's how they started defining. And this is, I would say, really extremely rational guess, a common sense guess, I would say, to have. I mean, if I have lived for uh, 20, 30 into 365, like 10,000 days till now, and in each of these 10,000 days, all the 10,000 days, the sun has risen. That means it's a fairly good point that the sun will rise tomorrow again. Um, but if among this 10,000 days, 99, let's say 800 days, whenever it has been cloudy, it has rained after that. If I see the sky to be cloudy and it has rained after 15 minutes, um, that's a fairly rational case that, the probability of rain is given a cloud is 80 by 100, right? So the number of events divided by total number of possibilities. So similarly here that they have defined probability in this way, and I believe it's a very very rational first initial guess when understand there's a very huge difference between mathematics and probability. In mathematics we will never say that if there is cloud there will be rain, because it doesn't happen always, right? It's in mathematics the truth value of a statement is either 0 or 1. That's why mathematical logic is vastly is different from probabilistic or statistical logic. In probabilistic or statistical logic we have the quantum state, we have the intermediate state where we can say it can be 80%, it can be 60%, it can be 10%, it can be like pi by e or e by pi percent, right? So the reason is we are looking into the total number of options divided by the total number of available options, the total number of required options, or essentially it's so the whole idea is what is the probability then. So if that's the main question that we're trying to understand here. So probability therefore turning out to be a function is therefore a function of an event. But it doesn't make sense function of an event. So because to define a function we need a domain set and a range set, right? Or a codomain set. So what we do naturally is, so the whole idea is that probability is defined on a set, on a subset of sample space or event. Probability is defined on the subset of that event, on that subset, and it can be actually done for all possible subsets. But as I said here, that not all subsets can be given a probability, because Vitali set is one example when it cannot be given. So there are some good events, good subsets. So that's why we make a good subset. These are all built by Kolmogorov, okay? From Russia, the Russian mathematician I was talking about in the group yesterday. The foundations of probability are built by him, and this axiomatic approach. And that's where we come to the axiomatic probability approach. Don't worry, again we will discuss this over and over again in live class. Okay, until it becomes you start to think this naturally whenever you're given a probability problem. So that's why we need something. So we have a sample space. We have a sample space S, let's say. It's kind of outcome of all events. Oh, sorry, outcome of the experiment. So we start with an experiment first. E. Sample space, and we write it mathematically, right? We write it mathematically. This mathematical writing will help you count the stuff. Okay. So the next step is the event. Event E is kind of a subset, as Anisha was saying, of S, but a good subset. By good, we mean we can assign probability. Remember that. And what's next? So we need to define probability properly, right? And we can define probability on an event like we have done using classical probability, using the ideas of the mathematicians 200 years back, or yeah, 200 years back. So therefore we define something called the collection of all possible such good events. So we define something called event space. Let's call it F. Collection of all such good events. Okay. Now what are the properties this event space should have? That's a very important question. What are the properties this event space should have? I mean, the properties that event space should have is similar to the property that we think generally. Like if I say that I want to find the probability of a set A or an event E1, and I want to find the probability of an event E2, I can say what is the probability of an event E1 or event E2, or what is the probability of an event E1 and event E2 together, right? So essentially, and also from high school math that you can actually form any event using unions and intersections. Any event. Okay. So that's why event space has this. So I forgot the all the like exact mathematics. So let me search it for you. So yeah, I mean there is no shame in searching. Yes. Yeah. The collection of event space. Yeah. Yeah. Here they are using complementing and arbitrary union. But in general, yeah, they're using complementary and arbitrary union. But if you remember that in using De Morgan's law in set theory, you can actually get back the intersection using unions and complement, right? So we are saying that if I can find probability of an event of E, then we can then if we can find probability of an event E, we can find the probability of an event S minus E or E complement. That's natural. We can say negation of that, right? And if we find probability an event E1, E2, dot, 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 then we can find probability of we should be able to find probability of E1 union E2, dot, dot, dot. Now the question that you should ideally ask is why not some other constraint? Why not some other properties? That's the question you should all ask. Why not some other properties? That's the most important question. The reason is you can actually get all uh, subsets, all good subsets using this. That's a part of you will learn this in major theory. And one example we will learn here is we will look at it later on. Okay, that one of the most important questions that it leads to is this, and this is very important, that why we are, so in random variables, when we will learn random variables, we will first start with the idea of CDF, cumulative distribution function, and we will see that we are asking for probability of a very specific subset, minus infinity comma x closed. The question is that why we are only considering this specific subset? Why this specific subset? The answer lies that using the specific subset, you can actually, using this specific subset and the operations that we have mentioned here, we can actually get back all the points, all the points in the real number space. So this in measure theory are called as like atoms of that set. Using all those set theoretic operations, you can get back the fundamental parts. So these are very important, guys. I'm telling you, like, I'm just telling you as a story, but doing this exercise is I personally believe it was life changing for me when I try to understand this way. Okay, so that's why we need an even space. Okay, we need a space of all events. All of you understood? I mean, at least understood the idea. No need to understand problem solving, but understood the story, understood how we are thinking. That's more important. Vedant, Srini,
Yeah.
any questions? Any questions from your end? Superb. Srini? Superb. So the next question is this, that now probability is coming. How do we define probability? So now it's very easy. We are defining probability now as a function. We want to give a measure. We define probability as a function from f to 1, 0, 1. So we can write p is function from f, this event space f, to 0, 1. We are assigning a number. We are assigning a number of to each event. Good event, not all events. Right. This is all probability, guys. Simple, right? In this case, in this very specific classical probability case, again, I said I will discuss in this live class of the courses and with you in the future over and over again. In the classical probabilities case, it's very simple. We are given this discrete 1, 2, 3, 4, dot, 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 let's say. Let's, even if you can assume a countable set, but here let's assume it's a finite set. So this is the sample space S. Let's now talk general stuff. Okay. In this specific case, even though it was of this format, but if you consider each point P1, it will be nothing but P1, P2, P3. So you can also consider this as P1, P2, P3. It can be any element. Okay. The PIs can be any dimensional, but these are distinct points in that. This is a discrete space. So you can consider the discrete points. This is an S. So an E can be actually any subset. So let's define the even space first. So we can take the power set of S. What is the power set? It's nothing but set of all subsets of S, or collection of all subsets, or you can say set. So in other words, we can assign, probability to each and every set. Sorry, event. Okay, sample space is done. Event space is done. The next is the probability P. So probability we are defining. So what we are doing in classical probability, although we said that a probability of an event in is this, we will derive it in front of you right now. So we define probability of any event where E is an element, not a subset now, element of F. Remember that. Yes. Questions? Unmute yourself. Yeah, Ishwan.
Yeah. So when we are considering event space,
Mhm.
if we are, let's say in this case, we are assuming a power set of S, but principally in a sample space wouldn't like in its own essence yield an event space since we are considering probabilities like P1, P2, P3.
Uh, oh yeah, I mean in this case, yes. In this case, that's why we are selecting it, but not always. As I
No,
said,
but okay, like except a few, but principally in common nature, if you're considering a sample space, we would in any way we'll have P1, P2, P3, which constitutes as event spaces only.
yes. Okay, so here's a so you are thinking discretely, and in discrete space, yes.
Yeah, yeah.
But as you will look into continuous random, that's a very good question. Is you think of continuous random variable, or if you would even think of an infinite space, understand this Ayushman very carefully. If you think of an infinite space, okay, imagine the set of all natural numbers. Okay. Um, even if like if you imagine the all space of all natural numbers, okay, imagine that you have let's very small probabilities on each one of them.
Hmm.
The sum of probabilities of the entire sample space will be what?
Technically, natural
Infinity.
numbers are infinity. Yeah,
Exactly, but it cannot be, right?
yeah.
So it will be zero, right?
Hmm.
Each element, or at least most of the elements.
Yeah.
So now if you define for most of the elements is zero, the sum of every event will be zero probability,
Hmm.
right? So that cannot happen, right? So that's why the whole idea of this minimal sets come in. We use those minimal sets like this to define it so that we can go down and we can go up, anything. And these are called Borel sets. When you do measure theory, I'm not going to tell you these things, but the questions you're asking are very fundamental. And that's why we needed this whole more than probability idea. But we are not going to discuss that. But that's a very good question. The whole idea is that we cannot define like that. So that's why we need specific subsets to specific events to define that, like fundamental events. Okay. And that's why these ideas came up, which can uniquely define
So,
it.
so by that logic, this is only applicable for discrete
Yeah.
instances.
Yeah. So that's why I take a discrete instance to motivate that idea to you. Later on, we will, when we go to continuous space, we will see that there's a different way of thinking there. But it's very
Understood.
fundamental. It's very fundamental. I mean, if you think of an infinite space, the probability of every event is zero, kind
Yeah.
of. Then how do you define a probability of subset? Because the probability of the subset will be sum of all the zeros. So the whole idea is that when you're adding zeros, to get a zero, you can only add countable number of times, not uncountable number of times.
Hmm.
So, I mean, what I'm saying is that there are different types of infinities. Okay.
Yeah.
So that's a beautiful part. So there's a countable infinity, there's the infinity of the natural numbers, and there's an uncountable infinity, that is infinity of real numbers, you can say, or something less than that also. The you can, in some of the zeros, you can only, the sum of the zeros is zero. In other words, how do you sum up in infinite? How? Okay, so this is a very good question. So let's understand this mathematically. How do you define a sum of infinite elements? You don't define it. That's why so that's where the beauty of calculus came in. We don't define it infinite sum of elements. We define it very interesting. Anyone knows that? How do you define a sum of elements, infinite sum of elements?
I
It is
mean,
countable.
we.
Define it as element of the partials.
Perfect. Very good. So we do not define infinite sum, Vishwan. We
Mhm.
define it using partial sums, or rather we define it countable. So what we do is we have infinite elements, let's say x1, x2. That's a very good question. So as I said, the question you thought was unimportant was the most important part. Okay. So please do ask, like keep on asking questions. In So what we do, we have x1, and then the x1 plus x2, and then we have x1 plus x2 plus x3. This is called partials, and we keep on doing this. So we get a sequence, right? Let's call it y1 or y2, dot, dot, dot. And we see that limit. Where is the limit going?
Yeah. We can do the same with integrals, I believe.
Sorry.
We can do the same with terms of integrals.
Exactly, we are doing that in some of terms of like it's the definite integral, rather indefinite integral, right? So we are doing integral from, exactly, integral of, let's say, 0 to x, and then for indefinite integral we are tending, because the output will be a function of x, tending x to infinity. Yes, so that's why we will see that to do that we need a space where it's integrable.
Mm.
Okay. So that's why this specific subsets come up. Not all over, not over all subsets you cannot actually integrate. That's why probability theory is very much integrated related to calculus real analysis. But I'm going to discuss this. I'm not going to discuss this in my classes because this is too much of a high concept, and we will have school students and different students. But I would always appreciate questions like this so that I can discuss after the class. Make sense? So please ask me questions. What
Yeah.
I'm saying that your questions have the secrets that you probably have been asking for the last 50, I don't know, whatever, what is your age, 10 years, 20 years, 5 years. But yeah, so very interesting. I hope it's clear, Aishwan.
Yeah. Yeah.
Okay. And probably this, yeah. Okay, great. Um, Now it's the age of ChatGPT, but these are the questions I have to understand by reading books and books and books. If you ask these questions, ChatGPT it will answer you probably in a few minutes or seconds after a few discussion. So please use that too. Okay, Srinivas, Ayushman, Vedant, and Anisha, all clear, guys? We are good to go to the next step. I need to drink some water. Okay. Sorry, Vedant and Anisha, all good? Perfect. Very good question, Ayushman. Very happy you asked this question. Okay, I believe person who asks great questions is the person who will move forward. Okay, so a probability is an element of f, and we are defining how do we define here in classical probability? We define simply by for, or we can call it x1, let's say, by x on each of the xk. I define it as 1 by the number of elements of s. So probability of any event turns out to be what? So now there is a, when I said probability, we forgot to tell you something. The thing I forgot to tell you, uh, hi Pushkar, you're a bit late. I have discussed a lot, but try to understand it when we move on to the next problem, or probably we will not have time to move on to the next problem. But I'm sure I have taught you things that you can do it in other problems too. So probability of any event E will be nothing but, okay, so what one property we have forgot, or a few properties. So probability, you can think of it like a mass. Okay, so when you're so it's like similar to counting. When you're, probability is kind of a measure, is a measure or mass of a set. So what properties do a mass have? If you have a phone and a bottle, and if you consider their volume or mass, I mean, it's a set A and set B. So probability of set A union B is nothing but probability of A plus probability of B, given that they are disjoint. Okay, they are not connected to each other or overlapping. Okay. Uh, so probability of A union B is probability of A plus probability of B if A and B are disjoint. What other probability properties are there? Let's see. Oh yeah, yeah. Probability of the entire sample space S is 1, actually. Okay, so we have got it. And here probability is nothing but probability of E is nothing but, let's assume E as a specific subset. Let's say y1, y2, dot, 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 yk. So we find out that probability of E is nothing but by this property. It will be nothing but probability of x y1 plus dot, 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 probability of yk, which will be nothing but each of them is 1 by s. So it's 1 by s plus 1 by s dot, 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 plus 1 by s k times. So it will be k divided by total s, and k is nothing but the number of elements of this, right? So it's this divided by s. So that's where, so you can say it's n of e divided by n of s. So what it turns out to be in classical probability is very important. In classical probability, it turns out that finding the probability is equivalent proportionally to find the number of elements of the event set. This is important because it turns out, what I want to tell you is, it turns out that therefore combinatorics, that is the permutation and combination, all these things, combinatorics is nothing but the art of counting sets, or it's the study mathematics of counting sets, counting number of elements of a set. So it turns out that classical probability is nothing but combinatorics, is equivalent, is mathematically equivalent to combinatorics. Okay, this is very important. That's why we put combinatorics and classical probability together. And this is very, very important, more than I can tell you to understand. And this also reinforces one important idea, that a probability is kind of similar to the counting function. Probability is similar to counting elements. The counting function, what I meant is n of e. Okay, the number of elements of a set. So the next question comes up to be, how do we count sets? We already done in our high school days counting, right? A lot of counting, a really hell of a lot of counting. But is there a relationship between counting sets? Is there a relationship between counting sets and probability? And the answer is yes, we have already understood this. But is there a relationship? Is there a common relationship, a common way to integrate them? And yes, there is. There is, absolutely. We will see the addition principle of counting has an equivalent of addition principle of probability. The multiplication principle of counting has an equivalent of multiplication principle in probability. And one thing that is never taught to you, in fact, there's something called the subtraction principle of, it's just nothing, negation of it. Okay, what is the negation of it? A negation of it is when you're counting 1 minus, so you can say there are mostly two of them, addition and multiplication. Okay, again, this comes from the very fundamental of numbers. When you have two numbers, two integers, I don't know, those are from math background. When you have an integer set, you see what operations makes it, like what operations on integer can actually make it integer. addition, subtraction, multiplication, but we also have something called division principles, only for those cases where it's divisible. So it's kind of, you can say that multiplication and addition are the most important thing, but we have the inverses of them, inverse operation of them, division principle. But yeah, this is not so important. The multiplication and addition are mostly important. Okay, so I will reduce its size. And we have, but when we combine them, their combination is also there. Unfortunately, there is no such name in counting, but there is a name in probability that is called law of total probability. That's nothing but combining is equivalent to law of total counting. You will never find something of law of total counting. It's nothing but combining the addition and multiplication principle together. And there's a very beautiful diagram. And this law is nothing but, if you, this law is equivalent to, you can actually build this law. All this tree diagram is nothing but this law. And this tree diagram has a correspondence to the circuits. When you build circuits in a, so you can say in kind of the same way that parallel circuits are equivalent to disjoint events because one doesn't affect the other, and sequential circuits are equivalent to multiplication principle, you can say, or because one is dependent on the other, or you can say conditional or multiplication. You will see conditional is very related to yeah. So one is disjoint, that is addition, and multiplication is conditional. Why I'm telling you, because this, when you try to think like this, it will change your mind of how you think. And this tree diagram, therefore, is the fundamental, I would say, mathematical or diagrammatic equivalence, or the Feynman diagram of law of total probability. And law of total probability is actually how you count all the probabilities, or actually how you find out the probabilities or count. All these years you have been doing this without knowing this. Okay. And you will see that this law of total probability and its tree diagram and addition principle and multiplication principle is the only way to do probability as of now, to at least find the probability. You have to, like I was telling you, that if you just search reinforcement learning, which is like the, I know you, I hope all of you know about reinforcement learning. If you search about reinforcement learning and just PDF, if you just search about it, um, this Sutton, this is a person who wrote this best book, and you will see that it's a really hard complex mathematical. Okay, it's what you will see, that it's nothing but tree diagram. See, if the Stanford's professors are doing this, that means there's some importance, right? I mean, the equations, the Bellman equations, and all these things that you see are not at all um, like yeah. I mean, these equations you see, it's like not trivial at all. But this is a fundamental of AI right now. Actually, it will be soon. So you see, and they're doing this. They are calling it backup diagrams, but essentially what they're doing is, it's a tree diagram. These are parallel circuits, and these are sequential circuits. Rather, these are disjoint probability events, and these are sequential conditional events. That's why one is dependent on another. Like a branch, one branch is dependent on the previous branch. Similarly, it's conditional probability, it's sequential. Just like current cannot pass from A to B if the one of the circuit switches are turned off in a sequential circuits. Similarly, it cannot happen. And these are two are mathematically connected. Let's not discuss the mathematics over here, but what I'm saying is that think in this way. Whenever you're thinking of a problem, think in this way. That's the way to think of. That's the way to learn. Okay, all of you got it, guys. I hope, I'm sure you probably didn't ever hear about this before. Okay, because I have never learned it. That's why I'm teaching, since nobody has taught me like this. But I hope it's clear to all of you, all the people out here. Yes, Srini, Ayushman, Anisha, Vedant, Pushkar. Okay. So hi Suvid, you were a bit late, quite late, but we are discussing this problems out here. But again, coming back here, As I said, if the tree diagram is nothing but, where did the tree diagram go? Oh, here. This is a tree diagram actually. So we counted the elements here. So therefore, we have discussed that probability, classical probability is equivalent to counting. And so therefore, we need to find the n of e, the event here, this one. So what is the n of the, what is the element of the event here? What is the, what is the size? What is the n of e here? The n of e is simple, but you can actually find out in an easy way that, I mean, you can use two different ways to find n of e. One is counting the elements. You can see that the red part and the blue part are, red part is equal to blue part. Okay, the elements. And you can see that there is a dark, like middle part, let's say y is equal to x part. And you can see y is equal to x part, the number of elements of y is equal to x part is how much? 6, right? 6 of them are there. Naturally, it's the number of, it's I comma j is the same value among all the possible dice outcomes. So there's 6 dice outcomes, so it will be 6. And red part is equal to blue part. And you know the whole total amount is. So n of red part plus n of blue part plus n of y is equal to x part is 36. You know that. And you know n of red is n of blue, and we want to find n of blue, n of red. So it's 2 times n of red plus n of y is equal to x is 36. And we know y is equal to x is 36. N of y is equal to x is 6, sorry. So n of red will be nothing but 36 minus 6 divided by 2. So it will be 15. So why I did this like way is because it teaches you one important principle, that is the symmetry principle. Don't have to count in a hard way. This is one way to find it, guys. Okay, this is one way to find it. Another way is to find it is just using basic like counting. Both are valuable. So you can say that for the first ni less than j, let's see the greater one. So how do you think about that in I greater than j? So you can say that it's very interesting.
This I is the x-axis, is it?
I is x-axis, yes. So how do you do it using a combinatorial way? I less than j. It's simple.
It will be that upper triangle, no?
Yes, it's upper triangle. You can count it, but can you do it in a quick, interesting, interesting combinatorial way? It's upper triangle, absolutely. If you're choosing any two elements out of this,
We can probably choose 1, 2, 5, and then based on what we have, kind of a summation thing, we choose.
yes, that's another way. So you can say 6 plus 5 plus dot, 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 1. That's one way. But you can, my favorite way is to think like this, is that if you choose, if there's a set of this 36 elements out here, 6 elements out here, 6 elements out here, if you choose any two elements out of this, so this is something called bijection principle. So you're mapping, or there's a one-to-one relationship with two sets, E and F, and that mapping, that relationship, and like where F is easier to find. So in this case, you can say that you can do this thought experiment, that choose two elements out of 1, 2, 3, 4, 5, 6. Assign the smaller one to be I and larger one to be j. Observe that if you do this, it will cover all possible I comma j pairs, right? So this is F. F is nothing but choosing. F is nothing but I comma j, where yeah, F is nothing but choosing. F is found by choosing. So F is nothing but choosing two elements of out of this, and it's a unique connection. So the number of elements of F is nothing but what? N choose 2. And since E and F are bijection, like there's a relationship, N of E is equal to N of F is equal to N choose 2, or 6 choose 2. So 6 into 5 by 2, which is 15. Make sense, guys? All of you? So this is important principle. Ayushman?
Yeah, I'm thinking of if I choose like some other values, then
Yeah,
that won't
think
give me
thought
15.
experiment. Please tell me what you're thinking. Let's say you don't think about I comma j. Let's say you choose two numbers, 5 comma 2. Or do not think of 5 comma 2. Let's say you choose two numbers. When you're choosing, there is no order, right?
Hmm.
5 and 2. Since there is no order, that's the best part. Since there is no order, you can
But
assign 2 to the smaller one, and you can. So 5 comma 2 is equivalent to 2 comma 5, or rather I comma j, where I is less than j. That's what I mean. So it's like there is no order, but you can make it ordered with a condition. And the
this is
condition,
so that just becomes ordering it.
yeah,
I
but with a
mean,
condition.
yeah, condition is that I is smaller than J.
Exactly. But in a set, it's not conditioning, right?
Yeah.
When you're choosing, there is no condition, but you're making it conditioned with an order, or order with a, sorry, when you're choosing a set, there's no order, but when you're making an order, you have to put a condition, because when you make an order 2 comma 5, it can be either 2 comma 5 or 5 comma 2.
Yeah.
So we are just choosing one of them, that is I less than j. Yeah, so this is something you learn by practice, but my job is to put the idea as a seed of thought in your mind. Like, sometimes you will solve a problem and think, Sri told us this, so can there be a bijection principle? That's the job of a teacher, to put that seed of thought in your mind and do it so many times that it naturally comes up to you. So we'll do it.
Basically, the principle allows us to parameterize like our sets. Like if I'm choosing, if I have a set of like one or two, now I just give a condition. I'm basically placing multiple conditions so that I can get a concentrated value. Like if I'm saying one and two, or like let's say for example 2 and 3. Now I'm saying I am choosing that I is smaller than J. So 2 and 3 is valid. Like otherwise it won't be valid.
Yeah, in this case, yes, it
Yeah,
will
in this
work
case,
for a
yes.
largely varied amount of problems, but in general, but you are kind of right. Like, um, when there's a set E, you try to enlarge the set E to a larger set where there is freedom, which is easier to count, and then you reduce down it to with
Hmm. Yeah,
constraints. So that's a very good observation, I would say, Aishwan.
understood.
Any more questions? So your job is now to solve the other three problems using the same thought I have discussed with you. So all the other three problems. Okay. So would you do that for me? Rather
Is
for
the
you?
is the document accessible?
Yeah, I've shared in the WhatsApp group,
Right.
each of the WhatsApp group. Make sense? Okay. Thank you for your time. Thank you for staying for 1 hour. And thank you for making my morning beautiful. So all the best, guys. Any questions?
Yeah, what time normally do you have these sessions? I'm just wasn't aware.
That's a very good question. It's same as asking what time I feel hungry.